The recording is on. So yeah, welcome to this meeting on the section 2 of chapter 4, which was on orthogonality. So the previous section we saw the basics of inner product space and what happens when you have an inner product space that is complete, and that's called a Hilbert space. And we had a lot of questions last time about, okay, what are these useful, what's nice about these? And today is sort of one of the big things, one of the main things that is useful about these inner product space is that you can define what it means for two vectors to be orthogonal. You can define what's the angle between two vectors, and in particular orthogonal is a very useful property, as we'll see, and basically we'll be seeing a few properties around that. So yeah, now that we're living in inner product space, we can define what it means for two vectors to be orthogonal. So we can talk about, among other things, orthogonal or even better orthonormal bases. So we all know from finite dimensional linear algebra that orthonormal bases are usually the kind of basis you want to be in. And we can also talk about taking a basis that is not orthonormal, orthogonal, and orthogonalizing it through a process that is usually seen in the first year's linear algebra course, and it actually still works in infinite dimensions. So in general we see that in finite dimension and in infinite dimensions orthogonal bases are very useful both mathematically and numerically. That's one of the new opportunities, that when you want to do this linear algebra in a computer, it's very helpful to have a basis that it's nice and stable, that you don't get error that accumulates, and that's something you get when you work with orthogonal basis. So I'll try and get some links with that in the following slides. So as a comment, most of the results in this section are actually valid for inner product space, and it's not usually the case that we assume that we have a complete space. So yeah, it's nice because we're only assuming that we have an inner product, not necessarily that it has it's complete with its metric. So yeah, if we have an inner product space with inner product defined like this, then we can say that two vectors x and y are orthogonal if, simply put, their inner product is equal to 0, which is equivalent, at least geometrically it has the intuition that we have two vectors that are perpendicular, but orthogonal is the generalization of that. And moreover, if we have a set of vectors in our space that has a property that any two vectors that are different are orthogonal and their norms is equal to 1, then we have what's called an orthonormal set. And some famous examples, at least in finite dimensions, is basically the canonical basis or the one-hot vectors, and they're trivially orthogonal. And if we step to sequence spaces, then same idea, the one-hot sequences also are orthonormal with respect to the inner product on that space. But we have some other examples that were more interesting in function space. So for example, if you take the set of continuous functions on the interval 0 to 1, then we have the Fourier basis defined as simply e to the I. So we have a set of functions defined as f of n is equal e to the 2 pi I n t. And because I here is a complex number, it's a cosine of 2 pi n t plus I sine of 2 pi n t. And this set of functions in this space of a function is also an orthonormal set. And indeed, it's actually an orthonormal basis, maybe up to normalizing these functions, but it is an orthogonal basis of this function space. And actually when we take the discrete Fourier transform of a function, we're actually expressing that function in that basis. So already we see an example of famous function families or famous algorithms that are equivalent to essentially expressing a function with respect to an orthonormal basis. So it's a little taste of things to come. And indeed, given any orthonormal set, here I have just some big K that may be finite or infinite, and a vector x in the span of these UKs, we can write x as a sum of a linear combination of the UKs, and we have a very nice property that lets us compute these alphas directly as simply the inner product between x and the kth basis vector. And this is pretty useful because in general, if you have a basis and you want to express a vector with respect to that basis, you have to solve a linear problem, and in infinite dimension it can be okay, but if you have a nil condition basis, it's a trouble. And in infinite dimensions, you have to solve an infinite linear problem, so it's even more complicated. But here in inner product spaces with an orthonormal basis, we're pretty good. We can just take the inner product and we instantly have the basis representation, and this is very useful. And it's one of the reasons why when you have numerical applications of these in function space, we try as much as possible to work in Hilbert space or inner product space, because getting a basis decomposition is so much more easier. And moreover, there's a theorem in the book that says that any orthonormal set is always linearly independent. So it goes back to this idea that, yeah, orthonormal sets are a natural way to get a basis for some stuff. But say you have already a basis, or at least a linearly independent subset of our space, we can always construct a subset that is orthonormal based on these x's by the following procedure, also known as the Gram-Schmidt orthonormalization. And the idea is very simple. You just take your first vector and normalize it, and that's your first u. And then for all the other ones, you just take the n, so xn, you subtract this term which accounts for all the contributions of the other previous basis vectors. So you take the orthogonal projection of xn relative to uk times uk. So what this term amounts to do is you take your nth vector x and you remove all the parts that are involved the previous basis vectors, and then you normalize it. And doing this procedure, you can actually construct iteratively or recursively an orthonormal set. And if it's a basis, then you have an orthonormal basis. Yeah, there's more properties, like the span of the u from 1 to n is the same as the span of the first n vectors in X. One note about doing this numerically, if you were to try to, say, get some vectors afloat and normalize them using Gram-Schmidt, you'd have a trouble. So there's a bit of a gap between what's done in practice when you work on a computer with these, is that this procedure is not stable. So you get a lot of errors, and so when you actually want to get an orthonormal basis, you have to do some other stuff. And for those interested, it's essentially what does when you do a QR factorization, that's how you can get a decent basis. Another interesting example, and very relevant actually for both numerical analysis and PDEs, is trying to find orthonormal sets of polynomials. So it's fairly easy to show that the set of monomials, so 1, t, t squared, t cubed, etc., is a linearly independent set in the functions that are continuous on the interval -1 to 1. But it's actually not orthonormal. And actually, even worse, numerically, it's very ill-conditioned. So if, say, you want to do polynomial regression and you try to do it in the monomial basis, for a large degree, you'll get a lot of trouble because this basis is ill-behaved. So actually computing the solution is very unstable numerically. So generally, when we try to get to perform some polynomial interpolation, we don't use the monomial basis, we use other bases which are orthonormal. And one of those bases is what you get when you apply this Gram-Schmidt procedure to the monomials, and you get what's called the Legendre polynomials. And the book goes into more detail about this, but essentially you can show that they satisfy this equation here, or this definition called known as I think the Rodriguez formula, where you define your polynomials as 1 over n factorial times 2 to the n times the nth derivative of t squared minus 1 to the n. And it's actually easy to show that these actually are, so Pn is a polynomial of degree n, and they are orthogonal with norm such as this. So really, if you have an orthogonal basis, it's trivial to get it to be orthonormal, so usually people don't bother. And sorry, no, I'll get to that later, but so Legendre polynomials are one way to get an orthogonal basis of your polynomials, but there's other ways. So another example is the Hermite polynomials, which are featured in exercise 13, which are another way to get an orthogonal set of polynomials. Over here, it's over L2 over R, instead of just the interval minus 1 to 1. And they are defined as the following, and when you look at this expression, it's pretty weird. You wouldn't expect it to be actually a polynomial, but actually, as the exercises make you do, it is in fact a polynomial. The trick is that when you take the nth derivative of e to the minus x squared, you essentially get a polynomial expression in minus x squared. So that then to get an actual polynomial, just multiply by e to the x squared, and so all these e to the minus x squared cancel out, and you're left with actually a polynomial. And another very famous basis is the Chebyshev polynomials, which again defined as something that does not look like it should be a polynomial, but actually it is. And all of these, so Fourier, Legendre, Hermite, and also I think the Chebyshev, they tend to show up as fundamental solutions of classical ODEs from physics. So for example, both for the Hermite polynomials and the Legendre polynomials, one of the ways they were originally found was actually trying to solve some ODEs from physics. And when you try to solve them, you find that actually you have a vector space of solutions, and these Legendre or Hermite polynomials actually form a natural orthogonal basis of your solution space. And this is actually a big hint to what's to come, as the idea of, okay, we have an ODE, and actually we can think of our ODE as a linear operator on a function space. And so when we find these orthogonal bases of solutions, it's pretty much as if we're finding an eigenvector basis of this operator that represents our operator. So we'll see that in later sections, but keep this in mind. And yeah, again, all of these are also not just for physics, but any numerical applications, you'd want to use these. So if any of you have seen, take a look at the so structured state space papers in I think there was a lot of discussion of these in math. In the structured state space paper, you see that they also talk about Legendre polynomials, Chebyshev polynomials, or Fourier polynomials. That's not it's not a coincidence. It's because these are particularly nice bases in which to express your functions. Now the final part of this section, which was fairly short, but I didn't have too much time to do these, is that, okay, if we have some subspace of our inner product space X, we can define what its orthogonal complement, so y bottom, is. It's typically defined as the set of vectors in X such that the inner product xy is equal to 0 for all y in our subspace Y. And one way to think about this is that we are actually generalizing the notion of hyperplane. Because say that our subspace Y is just a single one-dimensional space. Then saying xy equals 0 is simply saying, okay, we can take any vector either on our linear one-dimensional subspace Y, and then this is essentially the equation of a hyperplane, but it's a hyperplane in infinite dimensions. And so really what this definition generalizes the notion of hyperplane, or at least linear subspace, or it again goes back more to geometry. If I had more references on proper uh, analytical geometry, I could build on that, but unfortunately you're not my undergrad student, so I can't. But yeah, keep in mind that there is that geometric intuition between these that it really it's kind of like the generalization of a hyperplane. And it has a few interesting properties, and actually all of these are to be part of the exercise, and they're pretty easy to do, so I encourage people listening to try and do them either now or during a discussion. But among some very useful properties, we have that the orthogonal complement is always a closed subspace of X. Note that I think this is regardless of whether X is Hilbert space or not, so a useful property. We also have that the intersection of Y with orthogonal complement is always the zero vector, so they have no vectors in common apart from 0. We also have that Y is always a subset of the orthogonal complement of the orthogonal complement. And the only case when you have the inclusion in the other side is when Y itself is closed. That's another thing to think about. And we have other properties about inclusions of different subspaces. And another property that the orthogonal complement is equal to the orthogonal complement of the closure of our subspace. Yeah. So I encourage people to try and do these exercises because they're fairly easy and they're the most palatable exercise of this section, because I found that this section had a few exercises that were either very long or a bit bullshit to me, to be honest. So yeah, so to conclude this fairly quick recap, we see that stepping into these inner product space is already giving us some benefits, because if we have an orthogonal basis, then getting the basis decomposition for any vector is tractable. That does not necessarily mean it's easy, but it means that at least mathematically you can write it down. It has a nice closed formula, and you can usually get an exact solution without too much work. But it's also tractable numerically. And this is one of the big things, is that when you perform something like a PDE, when you try to solve a PDE, usually what will happen is that we'll choose a basis of function, say the Fourier decomposition, and we'll decide, okay, how will I approximate my actual initial condition or my functions in that basis up to some k. And hopefully that's a good enough approximation, and then because then you have a truncation of your infinite basis decomposition, you end up with finally just a finite dimension linear problem. And so that's how in practice most PDEs are solved, is by just reducing your original infinite dimensional problem to a finite linear problem, or a finite dimensional linear problem. And then again you have all these considerations about how stable your solution will be with respect to your basis, and again that's why orthogonal bases are very important. We get hyperplanes of vectors in the same space as our vectors. That's another thing important, that because we're in an inner product space, the dual space is essentially the same as the original space, which is not the case in general. And we have some connections to famous ODEs and PDEs from physics. So again, this hints at what we'll see later about more the spectral decomposition side, but that really most ODEs or PDEs, if they're linear, you can think of them as just a linear equation in function space, and then you can try to ask, okay, what are the eigenvectors and eigenvalues of this linear operator that defines my equation? And when you do that, you get some essentially fundamental solutions that are very useful to express. So yeah, before we move on to the discussion, I just have a quick PSA. So from now on, the meetings will be scheduled by default on Sundays at the usual time. So apparently it's 20 GMT. It's mostly because so few people are actually filling out the when is good, and we still end up at the same time anyway. So I figured, why bother? And another point is that the next meeting, at least unless someone is willing to do these recaps in my studies, that the only next time I can do these is on the 23rd, so in a couple of weeks. So I can do it next week and I can do it the week after. So unless someone is willing to do a recap for either next week or the week after, it will have to be on the 23rd. And also, since we've started this reading group in the summer, quite a few people have joined that weren't here in the beginning, so I hope you've been able to follow, but I do want your feedback. Lately I've been actually doing slides and doing more work for these meetings, but one thing that I kind of like is, okay, any feedback, so how you're finding these meetings. Is there anything that I can do to improve, or that you wish or was done differently? So yeah, I'm asking for feedback because it's very hard to get. So yeah, that's all I had for today. Thank you very much.
Thanks.
Thank you.
I think with respect to feedback, it might be a better use of our time to just like have everyone talk about the part that most confuses them, or like to talk about the part that most confuses them, and then maybe to split into groups that discuss that with each other. But not sure. Do other people like the recap? I mean, I like it, but I don't know if it's the best use of time.
I mean, I think a lot of people like just read the material like in the couple of hours before the meetings. So it's sort of one of the reasons I decided to do these recaps in slide, and also because I found it was better than just scrolling through the document.
Yeah,
I like it. I really been keeping up with the reading, so
yeah, it's been difficult to keep up. Any other comments from the silent people in the audience? Or we can actually move on to the discussion proper. I mean, I guess as far as confusing stuff, there wasn't too much to be confused about in this, because it's mostly stuff we would know from basic linear algebra.
Yeah.
Okay. Yeah. With regards to the suggestions, I like the idea of having people discuss what confused them the most, but for that I need people to actually tell me what they were confused about, or at least to say what they're confused, because it's like I'm doing these on my free time, and that's not a problem. But if I don't get any feedback, it's pretty hard for me to steer the discussion into something interesting. So it's also a bit of a plea for people to do or participate a bit more actively, or at least as actively as they're comfortable with. Because if I'm the only person talking and it's science, it's not super entertaining. Entertaining.
Yeah.
This list of properties sounds like it shows a pattern that's gonna show up in many different places in mathematics. Is there some way to describe this pattern in few words?
I think. I mean, it's if you think about it, taking the orthogonal complement is kind of a duality relation, because I mean, it's not exactly the case, for example, that y is equal to the orthogonal complement of the orthogonal complement. But
probably the orthogonal complement taken 4 times is equal to the orthogonal complement taken 2 times.
I think it would hold if you take so the orthogonal complement taking because when you take the orthogonal complement the first time you get a closed subspace. So really the reason why this does not hold, this is not an equal sign, is because Y might not be a closed subspace. In finite dimension, it's fine. It's always the case that you have a closed subspace, but in infinite dimension that might not be the case. And so this becomes an equal sign only when Y is already closed. So indeed, when you take this, so the orthogonal complement of the orthogonal complement, it's already a closed. So if you take its orthogonal complement 2 times again, then it's the same.
So instead of 2 equals 4, I should have said 1 equals 3.
I think there's probably a connection between that and stuff from so I think it's Topos theory. So around the general area of category theory, and this is sort of the very basic idea of Topos is that you define logic, but you define logic on a universe where you don't use sets. So you know that classical logic sort of works the way it works because it's based on sets. But if you were to say I'm using something different than sets, so for example maybe closed sets in a topology, then the intersection of 2 closed sets or the union of 2 closed sets might not be closed or something like that. And doing that, you can sort of say, okay, what's the equivalent logic that you obtain from that? And it's actually one way to define, okay, using these sort of kind of like sets, you get something different than just classical logic. So for example, I think if you use open sets, you basically get intuitionist logic. And if you use closed sets in place of sets, I think you get I think it's paraconsistent logic. Not 100% certain, but there's this whole idea of topos is that a general way to get logics, and that may or may not be multi-valued. But this is a bit further even more than what we're talking about.
Is an inner product the least amount of structure that you can throw on in order to be able to talk about orthogonal complements?
I think so. I mean, you can talk about the orthogonal complement if in your general Banach space, but then your orthogonal complement is not in the same space, right? Because it's a set of linear maps on your original space. So unless you use something, I think it's the Rees representation theorem that say, okay, any element of my dual space, I can find an element of my, no, it's not element. So if you take the dual of the dual, so you have your original space, you take the dual, and then you take the dual of that. There's a theorem that says any element of the dual sort of corresponds to an element of the original space. But I think there's some peculiarities in proving that, and it might not hold in general. Okay, any other questions?
How's that theorem spelled again? Rees representation theorem?
Yeah, so RIESZ.
Oh, yeah, okay.
It's a pretty famous theorem in just linear algebra, but I think it's actually to be seen in the upcoming sections, so we'll definitely be talking about it. Oli, you want to say something?
Nothing super specific. I didn't do all the problems in this one yet.
Me neither. I think these last ones I did them all because they're fairly easy, but the mean one is the one about Hermite polynomials. That one is a bit of a pain in the ass.
Yeah, I sometimes feel like I'm getting worse at math as time goes on because I do less and less calculus. So like integration by parts, I have to like think about it, and it's like so annoying.
I mean, I found it difficult as well, and I've been doing all the exercises, so don't feel too bad. I think it's more that this exercise in particular was a bit nasty. You can cheat and use Mathematica. Boo, boo, shame on you. Real mathematicians just do it by on paper with a pen. I'm joking. But yeah, I think unless anyone else has questions or we want to discuss the exercises, we can call it a day.
Oh, I have one question for the upcoming part.
Yeah.
So like the thing, are there practical applications to the thing where you like find the uh optimal the optimal point for like a convex approximation problem? Like I mean probably, but like do you ever compute that explicitly? Like find the solution to like projecting something onto a convex subspace?
So actually, yes. I think you can find. So one of the reasons is that when you have a projection problem on a convex set, it's instantly easier to solve. So generally, when people have problems in function space, they try as much as possible to get it formulated in terms of these kinds of problems so that they can actually apply the solution. But to give you some more concrete example, I do believe in control theory people do that sort of stuff. But another example is optimal transport. So optimal transport is this problem if you have one distribution or you have a heap of sand and you want to transport it to some other place and you want to and say that you want to optimize the way you transport each grain of sand so that you do the least amount of work. And a more mathematical example would be, okay, I have one distribution, I want to deform it into this other distribution by performing the least amount of work. So each I have to deform my distribution the least with the in the sort of the least effort. And it's interesting because the original formulation of optimal transport, which is this general problem, was not convex. But then later people found an actual convex way to represent it. So then, because you have a convex problem with linear constraints and actually a linear objective function, you can use these techniques. And so anything, so if you know anything about, say, the Wasserstein distance, to compute a proper Wasserstein distance, you would use these techniques.
Cool, thanks.
I'm glad I managed to have one question that I managed to that I already knew the answer in advance, because usually people ask me these questions, these advanced questions, and I'm like, yeah, I think that might be the case, but I would have to check. So this time I didn't. I'm pleased.
I have a question. Does P equal NP?
Yeah, unfortunately I'm not an oracle, so I don't think this is off topic. Sorry. Okay, folks, I think we can call it a day. So as always, I'll put the recording fairly soon. So.
Yep.
Great. Thank you.
Bye.
Thanks. Bye.